So now I'll move on to the second test mentioned in the lecture title. This is the root test. The root test. Okay, so as with the ratio test, let sum an be any series. The difference here is now we're going to let L be defined to be the limit as n goes to infinity of the absolute value of an inside an nth root. So what's the conclusion? If, first case, L is less than 1, then the series sum an converges absolutely. And in particular, converges. So remember, absolute convergence implies convergence. Second case, if L is greater than 1, then the series diverges. Third case, if L equals 1, then the test is inconclusive. So if L equals 1, the root test tells you nothing, just like in the case of the ratio test. So what's the intuition behind this? So if we look at this limit L, so L is equal to limit n goes to infinity of the nth root of the absolute value of an. So this would tell us that for large n, the absolute value of an is roughly L to the n. So absolute value an is roughly L to the n for large n. So hence, the sum of the absolute values behaves like a geometric series with multiplier L for large n. So this sum of absolute values of an, its tail, so the terms for large n, the sum after a certain n, starts to behave like a geometric series. So if we look at the cases, we get this L less than 1 corresponds to this absolute value of R less than 1, etc. Okay? So the intuition for this is very similar to the intuition for the ratio test. Okay? The idea is that the tail end of the series starts to behave like a geometric series, and this L is the multiplier. It plays the role of the multiplier.